If you did not do this using dimensional analysis, I would suggest using dimensional analysis, simply because if you're trying to use your textbook, you'll see that your textbook sets all of these up using dimensional analysis. And using dimensional analysis, we always start off with what's given, which in this case is this right here. We start with the 0.416 moles of K2CO3. And what are we looking for in this problem? The mass. And masses, of course, are measured in units of grams. So we set it up kind of a shell of a problem looking like this. Then what we need is a relationship that relates moles of K2CO3 to grams of K2CO3. And the reason for that is, on the bottom, what do we want to put in here for units? Yeah, we want to put in moles. And what do we want to put in on top? Grams. And why do we want to put it in this way? All right, we want to cancel out these units. So then what we really need is we need some numbers here. And this is kind of what we just spent our entire time doing these first 30 minutes of class, was calculating molar masses. Okay, and the molar masses are always the number of grams contained in 1 mole. Okay, so then we go back to the periodic table, we count up the number of potassiums, which in this case is 2. We count up the carbons, which is 1, and then how many oxygens? 3. And then we simply multiply these out based on their masses on the periodic table. We take the potassium, carbon, and oxygen. When we multiply these and add these on through, I have down here, was it 138.21? Okay. So now that we have these numbers, then where does this 1 go? All right, goes here in the bottom, and then the 138 grams of potassium carbonate goes on the top. We then multiply it through. We take the 0.416, multiply by 138.21, and we get that answer of 57.5. And again, most of us got this one correct. But any questions on this one? Okay, then the second one, there was a few of us that had more problems with this, but we started just the same way as before. We start off with what we're given. In this case, we're given 0.114 grams of mercury. What are we looking for in the answer? Moles of which stuff? Mercury. Good. And so in this one here, we want to cancel out units. What are we going to put on the bottom? And on the top, moles. Of course, then by definition, we're going to find the molar mass. And the molar mass is always the number of grams contained in 1 mole. Where do we get the number of grams? Where do we get this number? From the atomic mass. We go back to the periodic table. We find the atomic mass of mercury here is 200.59. We then put in the numbers. The number that goes on top here is how much? 1 on the bottom.
200.59.
200.59. Grams wind up canceling out. Then if we run this through our calculators, we're going to take 0.0114 and then what? Divided by the 200.59. If you do that on your calculators, you should wind up with an answer of 5.68 times 10 to the negative 5th. Why do you suppose I'm putting this in scientific notation? Because many of your calculators don't put it in that form. Because this number is one that is really what? Really what? Small, right? As a really small number, then we should take a really small number and put it into scientific notation. So any questions on this one? Okay, now, the portion of the conversion we didn't use is this portion right here. We could say that it also contains 6.022 times 10 to the 23rd. And if we had included it, what would the units on here be? Atoms, molecules, or formula units? These would be atoms because mercury is an element. The elements are made up of atoms. Which then takes us on to the next one here. Let's say that we have this problem. Let's say we'd like to know how many molecules are in 0.404 moles of H2O. So if we want to do one like this, we start off with what we're given, and we're given 0.404 moles of H2O. And what are we looking for in this one? Molecules. So again, when you look at these problems, try to ask yourself what you're given and what it is we're looking for. And specifically, we'd be looking for molecules of which stuff? H2O. Good. So now if we put down our facts, we could say for every 1 mole of water, we have how many grams of water? Well, for grams, we've got 2 hydrogens, we got 1 oxygen, 18.02. We did this one the other day. It's 18.02 grams. So 2 hydrogens at 1 each, or 1.008, and 1 oxygen. And then we want to put in Avogadro's number, 6.022 times 10 to the 23rd. The label on here is going to be molecules of H2O, because water is a molecular compound, and molecular compounds are made out of molecules. So now, if we want to put in a conversion, what are we going to put on the bottom? One mole. Right. We want to put in the 1 mole because we want to cancel out the units. Now, are we going to do anything with the 18.02 grams? No, we don't. We wrote it in, but we really didn't need this, because what we really want is we want to relate these two here. And how are these two related to each other? Are they the same or different? They're the same thing because we've got equal sign in here. So if this equals this, and this equals this, and these two are equal to each other. So what does that mean we can put in the numerator? 6.022 times 10 to the 23rd with a label of molecules of H2O. Moles of H2O cancel out. Now run these through your calculators, because sometimes we find out students have forgotten how to enter this in. Remember to use your EE button or your EXP button. So I'm going to do this quickly on my calculator here up on the display. I'm going to take 0.404, multiply this by 6.022, then you find that EE button, which on my calculator is right down here. Some of you have to hit that second function, and then I'll put in 23. So remember, it's not times EE, it's simply press the EE button or EXP button, and then the 23. You run it through there. Looks like we wind up with 2.43 times 10 to the 23rd. So 2.43 times 10 to the 23rd. And make sure you can come up with that number yourself on your calculators. Okay, any questions on this one? Yes?
So every time we try to compare molecules, you just use a 6.0 substitute.
Yes, because if we're going to calculate molecules, molecules are always going to be what kind of number? One that is really, really, no, big. We're going to have bunches of molecules. Remember when we dump out ping pong balls, that's going to cover the entire Earth 60 miles deep with ping pong balls. So if we're going to calculate molecules, we need a really, really, really big number. So that means we need to put a really, really, really big number on the top over here. And we should never calculate an answer that's really, 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 really big in units or grams, because if you had this many grams of something, then of course that's going to be something that's probably approaching the mass of the Earth. And who knows, I would have to sit down and do the calculations with that to confirm. But we can have really, really big numbers of molecules. See, any other questions? That was a good one. Okay, let's try this one. Let's say that we have a container of water. Holds, and this would be like a pint of water. Yes, Gabby?
I have a question for to the molecules. So
Yes.
Is that only if it's molecular, or?
That's correct. If we had changed this, let's say that instead of H2O, we had put in argon, or one that we haven't used yet. Let's say it was neon. Okay, if it was neon, then there would be this many moles of neon, and then this would be 1 mole of neon here. But we wouldn't have molecules of neon, we would have atoms of neon. And we put in atoms of neon because neon is one of the elements, and the elements are comprised of atoms. And then if we were dealing with an ionic compound, then the word that we put in here would be formula units. So it depends upon what we're dealing with. So if it's a molecular compound, we use the term molecules. If it's an ionic compound, we use the term formula units. And if it's an element, like we just showed here, then we would use the term atoms. Any others? Okay, good. Let's go on to this one then. A pint of water is about 473 milliliters. And what we'd like to know is, if water has a density of 0.998 grams per milliliter, how many water molecules are in the container? So first off, we're talking about a pint of water. A pint would be, I don't know, it'd be larger than a normal, there's about a pint there. That's actually, this bottle's about a half liter, I think, maybe 20 fluid ounces. But it'd be about that size. So an answer like that, if we want answer in water molecules, that answer is going to be really, really, what?
Small.
Big. It's going to be really big because we want lots of molecules in there. So before you even begin answering a question like this, you can ask yourself what type of answers are going to make sense. And if we're going to find the number of water molecules in a container like that, it's going to be a whole bunch of them. So with this particular one, we'd start off with what we're given. Now I see that there's 2 values here, but which one do you think would be the most sense to start with?
473.
473, right. We're going to start with the 473 milliliters of water. And what are we looking for in this one? Molecules of H2O. And again, this answer is going to be one that is really, really big. So, we want to work towards a really big answer. So, in order to convert to molecules, we haven't looked at anything that takes from milliliters to molecules. We're probably going to have to take this units of milliliters and convert it to units of what? Grams. Because we have worked with grams. So how can we convert this one to grams? D is equal to M over V. So if we want the mass, then mass is equal to the volume times the density. And this one we should even be able to figure out using dimensional analysis. If the density is 0.998 grams per milliliter, we'd put grams on the top and
Milliliters on the bottom.
milliliters on the bottom. And if we want complete units, if this is the density of water, this means that we have grams of
H2O.
H2O on the top over milliliters of which stuff? H2O on the bottom. So number of grams of H2O per milliliter of H2O. And the reason why we do that is because what happens to milliliters? They cancel out. Now we're left with grams of H2O. Well, now if we start writing down some facts, we wrote these down just right up here. We can write them down again. We could say that for every 1 mole of water, we have 18.02 grams of water, and this contains 6.022 times 10 to the 23rd molecules of water. Now the purpose of writing the entire conversion down like this is to help us determine what we plug in here. What do we need on the bottom to cancel out? What do these units need to be here? Grams. And what's the number that goes with the grams? Right, we have 18.02 grams, which is going to go in right here. And then the units that we want in the numerator are molecules. And you see, we have this conversion right here, this relationship where these two are equal. If they're equal, we can put one over the other, which means on the top we'd put in 6.022 times 10 to the 23rd molecules of H2O. At this point, grams of H2O cancel out. And then we need to run this through our calculators. We'll take 473, multiply it by 0.998, then times Avogadro's number. Remember how to put the Avogadro's number into your calculator at 6.022 and then hit the EE or the EXP button, 23, and then we divide that by 18.02. And if we do that correctly, we should wind up with an answer with how many significant figures? 3. So we'd round it off to 1.58 times 10 to the 25th molecules of H2O. And when we ask ourselves if this is an answer that makes sense, remember we were looking for an answer that is really, really big, and this then would be a really, really big number and should be one that makes sense. Okay, then here's our last one for the day, and then we're going to do some more practice. I have a bag of fertilizer. Contains 25.0 kilograms of ammonium phosphate. then we'd like to know what is the mass of phosphorus in the bag. Now this one here, we're going to kind of step back to how we started calculating these molar masses. Even though you may have been doing them a short way, this is one where it's more advantageous to show all of your work and write it out the long way. And so we're going to start by counting the number of atoms of each element. And we'll start by counting nitrogens. How many nitrogens do we have here?
3.
3. How many hydrogens? 12. How many phosphorus? 1. And how many oxygens?
4.
Okay, so then I'm going to show all the work here again. We're going to take 3 times how much? 14.01. We're going to take 12 times 1.008. Then we'll take 1 times 30.97. And then we'll take 4 times 16.00. Again, you're going to see the purpose for showing this the long way in just a moment. If we multiply each one of these through, we get 42.03. We get 12.096. Get 30.97 and 64.00. If we then sum these together, we'll take the 42.03, add to that 12.096 plus 30.97 plus 64. And we wind up with 149.10. And remember, we only go out to the hundredths place because these are only good out to the nearest hundredth. So now if we go back then and ask ourselves, what does this number represent? Let's say we put this answer in grams. This would be the number of grams contained in 1 mole. 1 mole of which stuff? Ammonium phosphate. Good. We'd put NH4PO4. And this would be the number of grams of ammonium phosphate. Now, of course, if this is in units of grams, that means that the units on each of these answers up here, like the 42.03, this would be in units of grams. Next would be grams. Then we'd have grams and grams. Because when you sum together, you can add together the masses in grams. And specifically, this would be grams of which stuff? 42.03 grams of nitrogen. Would have 12.096 grams of hydrogen. Would have 30.97 grams of phosphorus and 64.00 grams of oxygen. So these here represent those masses. Now here's the great thing about using those prefixes we talked about the other day when we have our metric prefixes. We can apply those metric prefixes any way we wish. Let's say that we took all of these here, all of these values, and we divided by 1,000. If we divide by 1,000, we have a prefix that's called 1/1000th, which is labeled milligrams. And if all of these here would be in units of milligrams, that means that this answer here would be in milligrams. And this would be equal to 1 millimole. Good, 1 millimole. So we could put in a millimole in there. We could just as well taken all of these here, and instead of putting them in milligrams, we could have put them all in kilograms. If these are all in kilograms, that means that this answer here would be 149.10 kilograms, and this would be the amount contained in 1 kilomole. Because again, we'd multiply everything by 1,000. Now my point in showing you this is, what are the units given in this problem? Kilograms. So what do you think the most advantageous units would be for us to use over here? Kilograms, and we would be calculating the amount of a kilomole. And so, if we do it this way, we can then start with our calculation. We'd have our 25.0 kilograms of ammonium phosphate. And what are we trying to find in this problem? The mass of phosphorus. And mass is measured in which units? Grams. Or in this case, it probably make more sense to calculate it in kilograms. And so we're calculating the kilograms of which stuff? Kilograms of what? Phosphorus. So then what we need to do is we need a conversion that relates the kilograms of ammonium phosphate to the kilograms of phosphorus. And we have that right here in this problem. These are how the two are related. We have 30.97 kilograms of phosphorus for every 149.10 kilograms of ammonium phosphate. And when we set it up like this, what happens to the units? And what cancels? Kilograms of the ammonium phosphate, and it gives us kilograms of phosphorus. So we then run this through our calculators. We take 25, we multiply it by 30.97, we divide it by 149.1. We wind up with an answer that should have how many significant figures? 3. So we'd round this answer out to 5.19 kilograms of phosphorus. Now once we get that answer, we should ask ourselves if that answer makes sense. If this is contained in a bag that contains 25 kilograms of ammonium phosphate, then we know that for sure our answer must be less than 25. And we have one that's less than 25. In fact, it should be about 1/5. So we take 30 over 150. 30 over 150 is 1/5. This should be about 1/5 of 25, and it is.